Hello dear students, welcome you all. In this lecture, I am going to discuss about the topic analog computations in physics, right? Analog computations in physics, you can see here. What is the meaning of analog computations in physics? Analog means we are going to deal with the analog signals. We know very well that analog signals are basically, continuously time varying signals. We can also call them as a continuous time signals, CTS, right? So in, this topic, actually we are dealing with the analog signals. That the one thing is clear from the word analog. The second thing is computations. Computations means we are going to do the mathematical calculations like addition, right, subtraction, right, multiplication, right, division, right, integration, very important, right, differentiation, right, all these mathematical operations that we are going to perform in electronics by designing different circuits, right? So this is the meaning of this topic, analog computations. Computations means mathematical calculations and analog means the signals that will be used in this method. They are analog, they are not digital, right? So actually analog computations are very, very important in physics. We know very well, we usually faces equations in physics like we can have a linear equation ax plus v is equal to 0. We can have a quadratic equation ax square plus bx plus c is equal to 0. Similarly, we can have a cubic equation, right? And the most important thing is that we can have a differential equation like f is equal to ma. Now I can express it as f is equal to m into d square x upon dt square. This is a differential equation, right? And if I want to solve this equation, then I can take the help of analog computations. I mean, I can solve it by designing an analog computer by taking the help of different components available in the electronics, right? We can have a much complex differential equation. This is a simple example. You can have any example right there, and when we will solve this equation by using analog computations, we know very well that we will have a very fast way of solving the equation. The accuracy will be very, very high. There is no chance of error. So we can actually simplify any equation that we face in physics by designing an analog computer, right? So how we will solve these equations? We know very well we have deal with the summing circuit, right, subtraction subtractor, right, integrator, right, differentiator, right, logarithmic amplifier, anti-logarithmic. All these circuits have been already discussed in electronics. And how these circuits are designed? They are designed by making the use of a operational amplifier. So operational amplifier is the heart of all computations, because operational amplifier can be used for designing a summing circuit, scaling circuit, averaging circuit, subtractor, integrator, differentiator, logarithmic amplifier, anti-logarithmic amplifier, wave shape generator. Any kind of operation can be done by making the use of a operational amplifier, right? So this is about this topic, analog computations, right? Now here I will take a differential equation and I will try to solve this differential equation by using this method. So let I have a differential equation d square b upon dt square, right, plus k1 db upon dt, right, plus k2 b, right, minus b1 is equal to 0. Let this is equation number 1. Now here This is a second order differential equation you can see here, right? Here in this equation, b is the given function that we are going to calculate, right? K1 comma K2, both these are real and positive constants, real positive constants, right? Whereas the B1 that is given here, B1, this is any given function, right? Any given function, and it can be a constant, right? But the thing is that we already know this function. Our intention is to solve this differential equation, and when I will solve this differential equation, what I will get? I will get v as a function of time, right? B as a function of time. This will be the solution of this differential equation because it is a second order differential equation. After solving it, I will get v as a function of time, right? So this is the purpose of solving this differential equation. B can be any physical quantity, right, involved in this differential equation. It can be a volume, it can be pressure, it can be current, it can be any physical quantity, right? So now I will design a circuit to solve this differential equation. So you can see here the circuit is given here. So you can see here the circuit that I have designed for solving this differential equation, right? In this circuit, you can see the different components are. This op-amp is going to act as a integrator. It is an integrator circuit, right? This is again an integrator, right? What is this? This is a summing amplifier. And this is again a summing amplifier. Right. So these are the different components that I have used for solving this differential equation. Right. In integrator, I have taken an integrator which is acting in the inverting mode. Similarly, summing amplifier is also acting in the inverting mode. Inverting mode means the input is applied at the inverting terminal. You can see here all these op-amp are acting in the inverting mode, right? Now, first of all, look at this differential equation, right? I can rearrange this differential equation. I can write it d square v upon dt square is equal to, right, minus k1 d b upon dt, right, plus b1, right, minus k2 b, right? So I can write it in this way also. Right. Now you can see here d square v upon dt square, this is equal to minus k1 d, I took it toward this side, plus b1, and I take this term separately, k2 b, right? Now let this is equation number 2, right? Now let this d square b upon dt square, this is applied at this terminal. Let's assume initially d square v upon dt square. You can ask a question that we are already applying d square v upon dt square at the input of integrator. So how we got d square v upon dt square? So I'm saying that let's assume we are not actually applying, but we are assuming that d square v upon dt square is applied at this terminal, and we know very well that according to equation number 2, d square v upon dt square is equal to this term, right? Now when d square v upon dt square is applied at the input of this integrator, we know the output of the integrator is equal to minus 1 upon rc, right, integration b input dt, right? Now rc, r this and c this, let's assume here that rc is equal to 1. They are chosen in such a way that their product is 1. Then I will get what? V output is equal to integration simply v in dt. So integration v in dt means negative also there. So I will get here what? Minus dB upon dt. For the sake of simplicity, assume that the constant of integration is equal to 0, right? So I got minus dV upon dt at the output of this integrator. Now this minus dV upon dt is applied to this second integrator, again through this resistance and this capacitor, right? So again the output of this integrator will be what? Again RC are chosen in such a way that RC is equal to 1. So B output here, it will be what? It will be integration of what? Minus dB upon dt. So what I will get into dt? What I will get? I will get simply V, right? Minus minus plus. So I will get V at the output here, right? At this point, right? Now this B is given to the summing amplifier. This is summing amplifier, but now come to this side. Now this minus dV upon dt is applied to this summing amplifier through this resistor R1, right? And the other input to this summing amplifier is a B1. We know very well that we also have B1, and B1 is a given function, and it can be a constant. It can be a fixed DC voltage, or it can be a given function, right? Now this summing amplifier has two inputs. One is this one and second is this one. We know very well that the output of summing amplifier, right, it is equal to minus RF upon R1, right, B1, right, minus RF upon R2, B2, plus so on. So RF means this R. Here RF is taken as R, right, feedback resistor. So we have two inputs, so two terms will be there in the output. So B output is equal to R upon R1 minus, and minus it will give me plus R upon R1, right? Because B1 is negative, so it is dB upon dt. You can see here it is minus dV upon dt applied directly from here. So minus minus will give me plus R upon R1 dV upon dt. Then the second term minus R upon R1 and B1, right? So I got this output at bit point, this point, right? This point I got R upon R1 into dB upon dt minus B1. This is the output. Now this output is applied to this terminal, right? Now again, this operational amplifier is acting as a summing amplifier. It has two inputs. One is coming from here and it is a V, and the second is coming from here and it is a this one, right? So now, what will be the output of this summing amplifier? Again, the same logic, R upon R2, right? R upon R2 into B. B is the, this input, so it becomes minus B, right? Then what is the next, right? The next is, second is R upon, here, R upon, I have not taken resistance here, so we should take a resistance here, because when we are applying input, we have to take resistance here. So let's consider a resistance here, right? This is let R. This resistance is again R, right? So but will be the second input here, result R upon R, right? It means 1 minus R upon R1 into R upon R1 dB upon dt minus B1, right? This one as it is, right, goes to here, right? Negative sign because RF upon R means R upon R is 1. Now this is the output that appears at this terminal output, right? This terminal B output, right? And this was B input. Let me take it down. Now you can see here what is the output. I can expand it and write it. It will become minus R upon R2 into B minus R upon R1 into dB upon dt plus B1, right? So I can write, we know very well that what we have written in the beginning, that this is equal to minus R upon R1 into dB upon dt. I have taken it minus B1 minus R upon R2 B. So why I have written it in this way? Because we know very well here minus K1 dV upon dt plus B1, right? This one, right? I can take minus outside, so in that case this will become plus and this will become minus, right? I can let's write it here, minus K1 dV upon dt, right, minus B1, right? So and then minus K2 B, right? So when I make this as per this requirement, now you can see here R upon R1, let's it is equal to K. So then it becomes minus K K1 dV upon dt, right? Then minus B1 minus K2 B, right? Now let this is equation number 3. This is, you can see from here, what is it? It is exactly same to this one, minus K1 dV upon dt minus B1 minus K2 B, right? So what does it mean? That whatever output is appearing here at this terminal, right, this output is this one, right? This output is this one, right? This one, right? Now we know very well that this output is equal to which? This output is equal to d square V upon dt square. So that's why I have taken this path from here to here. It is, I think, broken here, so I can join it, right? So it gets joined automatically, right? So you can see here, now if I connect this path to here, then d square V upon dt square that I assumed in the beginning, let's suppose, so there is no need to apply d square V upon dt square. It will automatically come from here, right? And it will be supplied at this terminal, because you know very well that d square V upon dt square is equal to this function on this side. So this is appearing at this terminal, right? And it is applied here. So in this way, we will get the solution of this differential equation. Now you can ask me where the V is coming, right? Actually, we were interested in getting V function of t. So you can see here, if I place CRO here, CRO lead here, then it will give me the value of B as a function of time, right? If I want to get dV upon dt, I can get dV upon dt by placing CRO lead here, right? Then I will get dV upon dt, and here I will get at this point simply I will get V as a function of time. So in this way, now this circuit is capable of solving this differential equation, right? The only thing that we have to apply, that we have to define B1. As I told you that B1 can be a constant, it can be a function of time, but it is given. So right, so we have to only apply V1 and the supply to the different operational amplifier, that is plus VCC and minus VE. The rest of the things will be done by this circuit. So in this way, I am able to solve this differential equation. So in the same way, any differential equation that you are given, you can simplify that differential equation by designing this type of circuit. But the thing is that we have to remember that we have to take the help of integrator, summing amplifier. But suppose you can ask a question that if in this equation in place of positive it was negative here, right, then what makes the difference? No. And then in that case we can use a subtractor, because it was a summing amplifier. In that case we will use the subtracting amplifier, because subtracting amplifier will reverse the sign, right? Or we can use in non-inverting mode also. So we have not to bother about the signs, right? Because signs can be dealt with easily by simply changing the mode of working of operational amplifier, whether it is in integrator or it is in summing amplifier, it is in subtracting amplifier, right? So any differential equation given to you, you can simplify it by using this method, right? So this is all about the analog computations in physics that I started and discussed here. So if you are given any problem, any differential equation, then I am hopeful that following this way you can simplify that equation, right? This method has wide applications in physics, right? As I told you that any physical equation that I want to solve, I can quickly solve it by designing a circuit, right? And the accuracy will be obviously very, very high as compared to the manual method, right? So this is all about analog computations. Thank you very much.